Okay, I'm going to start this lecture by looking at that one unresolved problem we had from the previous lecture. I hope you got a chance to look at it here. What I'm going to claim is that this limit, as xy approaches the origin of x cubed y cubed over x squared plus y squared, actually ends up being 0. So L is in fact 0 here. Okay? The idea is that the numerator and the denominator are both approaching 0. Okay, they're both approaching 0, but they're approaching 0 at different rates here. Notice the limit as xy approaches the origin of the numerator is 0, and the denominator is 0. So that this function itself that you're trying to find the limit of doesn't even exist at the origin, right? You're going 0 divided by 0, and there's no such thing. Okay? But I claim that the limit still does exist, okay? It's a 0 over 0 type form. You know that sometimes that those limits actually do exist, okay? Those limits actually do exist. Okay, what I'm going to start out is to show you that the limit is actually 0. I'm going to use the limit definition here. So how do we start out there? I'm going to just let epsilon be a positive number that's arbitrary. So epsilon is greater than 0, freely chosen, okay? Now, the next thing I'm going to do is say the distance between the point xy and the origin is r. Okay, I'm going to give that a name now. Okay, now remember we have upper bounds on this, which we're calling delta. Okay, I'm not concerned about an upper bound on that right now. I'm just giving it a name. R for radius is basically what I did. Now, remember, we're not concerned about what happens at the point 0, 0 at the origin, but only what? Around the origin. Okay? So I'm going to have that r right there be greater than 0, right? Okay, that just means we're actually staying away from the origin. Okay? Now, you know what this is? This is the square root of x squared plus y squared. So if I square both sides, because all these numbers are positive here, x squared plus y squared is equal to r squared, all right? Now, y squared is certainly greater than or equal to 0, so that means x squared plus y squared is certainly greater than x squared alone, okay? So that r squared is greater than x squared, taking square roots. That means the square root of x squared, which is the absolute value of x, has got to be strictly less than r, okay? The square root of x squared is absolute x, not x, right? Notice from the symmetry considerations here, exactly the same argument can be made for y. Okay, so if I call this distance from the origin to the point xy r, then the absolute value of x has to be less than or equal to r, and the absolute value of y has to be less than or equal to r. Now I'm going to go ahead and use these facts to make some arguments about this function up here and how big it is and stuff. Okay, what would be an upper bound on the absolute value of x times y? Well, we could just multiply these absolute values. The absolute value of the product is the product of the absolute values. So I could say the absolute value of xy is less than or equal to what? R times r is r squared. And then I could cube that value, and I would have r squared cubed. So we could actually have r to the 6th over here. The absolute value of x squared y squared is less than or equal to r to the 6th. This is getting at that what? That numerator up there. Okay? Now let's finally consider this then. The absolute difference between the function and 0. Okay? So this is f of xy minus what I'm claiming is L. Okay? Well, you can get rid of the subtracting 0 in your mind here. And the absolute value of a quotient is the quotient of absolute values here. Okay? X squared plus y squared is r squared from definition, right? Absolute value of x cubed y cubed we said was bounded above by x to the 6th. So this is bounded above by x to the 6th divided by r squared. That's r to the 4th. Okay? Now remember that I want this to be what? I want this to be less than epsilon, right? Okay? So if I take 4th roots of both sides of this, making sure I'm thinking of these as positive numbers, right? If I make r greater than 0 but less than the 4th root of epsilon, then what I can actually do is say, when the distance between xy and the origin is between 0 and the fourth root of epsilon, what I can actually do is go backwards and reason then that what? The absolute difference between the function and 0 is less than epsilon, which is just exactly what I wanted here. So what would be our delta in this situation? What would be the delta in our definition here? That delta would be the fourth root. I suppose I should have written this explicitly in black here. But the delta we want to use is the fourth root of epsilon. Okay? Oops, I almost wrote that backwards. Okay, dyslexic or something. All right, let's go on to another problem. Let's look at this one. I claim the limit as xy approaches the origin of 3x squared y divided by x squared plus y squared equals 0 also. Now the clue on this one, as is on the previous one, is I'm claiming both the numerator and denominator are going to 0, okay, as xy approaches the origin, but that this one in the numerator is actually approaching 0 more quickly than the denominator. That's the essence of this argument and the previous argument too. Notice, right? If this is getting small, this is actually going to 0 more quickly. R to the 6th is going to 0 more quickly than r squared as r gets small. Anyway, okay, let's start out on this problem. Let epsilon be greater than 0. That's arbitrary. Okay, and this time I didn't give this a particular name, but the distance between xy and the origin is less than delta. Okay, I've got to get some sort of hold on the delta there. I could have called that r again and proceeded just like I did in the previous one, but I'm going to do a slightly different argument here this time. Okay, let's just take a look at the absolute difference between the value of our function and the supposed limit that I'm calling 0. That is supposed to be 0, that is. Okay, this absolute difference. Notice that I could actually factor out the absolute value of y here because all the other factors are non-negative, right? 3x squared and x squared plus y squared are non-negative. So those can come right outside the absolute value signs, and we don't need absolute value signs around those. Okay, now just for some quick reasoning here, this is a little exercise for you. It's not much of one. But can you see why this quantity in parentheses is always going to be less than or equal to 3? Okay, can you see that? All right, let's just discuss quickly why. Well, you know that 3x squared divided by x squared would just be 3. Now, if I divide 3x squared by something a little bit larger than x squared, or larger than x squared, then I'm going to get something smaller than 3. Well, notice that x squared is always non-negative, so the largest value, or the smallest value that this could possibly assume in the denominator is x squared anyway. So that the largest value that it could assume is 3, right? Okay, and then just carried out this other factor, absolute value of y. Here I want to make this quick comment here. The absolute value of y, you notice, once again, like an argument in a similar example, is less than or equal to the square root of x squared plus y squared, right? Because once again, don't forget, the absolute value of y is what? The square root of y squared. The square root of y squared is absolute y, not y. Okay? All right? So if I add an x squared in here, it's going to be at least as large. So you see the direction of the inequality right there. So this guy is clearly that's less than or equal to this. Okay? Now, what do I want this to ultimately be? I want this to be what? This is the difference between my absolute difference between my function and my supposed limit. I want that to be less than epsilon. So I'm going to make this thing less than epsilon right there, and let's see what happens here. Okay? Well, what am I going to do here? Remember what I was talking about here? This is actually the square root of x squared plus y squared. I should write that in there too. That's a plus sign here. I'll make it look more like that. Okay? So right here, if I divide on both sides by 3 and say let delta equal epsilon over 3, then what we're going to have is that this is 3 epsilon is less than epsilon here, so that we have a conclusion we want in this particular case. So here's what we've got to do for our delta here. Okay, we just got to have delta be what? Epsilon divided by 3. Okay, because if epsilon is less than, or if delta is epsilon over 3, and this value is less than epsilon over 3, those look backwards from each other, then going through this reasoning, we can see here that the difference between the function and 0 is going to have to be less than epsilon. Okay, so it works. So we've got a proof there. Now let's go do a different one. Okay, let's take a look at this guy. This is very different here. The limit as xy approaches the origin of x squared y. Okay, so wait a minute. So that would be approaching 0. X to the 4th plus y squared, that would also be approaching 0 as we approach the origin. Nevertheless, I claim this quotient here as xy approaches the origin doesn't exist. Okay, so this is going to be kind of an interesting situation here. Okay, because I'm going to show you here there's an important fact illustrated in this particular example. First of all, I'm going to consider, like we did in the previous lecture here, consider approaching along different lines. Okay, let's see if I can show DNE by approaching along different lines. Suppose I've got this line y equals mx. Okay, so this would be a non-vertical line. Okay, so the non-vertical lines can be going through the origin can be written this way. Just go up here and replace y by mx everywhere, and then I'm considering what happens as x approaches 0. Okay, this is dandy because I'm now just considering a single variable instead of what? Instead of two variables. Okay, so I would have what? Mx cubed in the numerator. Down in the denominator, I would have x to the 4th plus m squared x squared. I could factor out an x squared. Okay, now let's now I'm not interested what happens when x is actually equal to 0. So let's divide out the x squared and consider mx over x squared plus m squared. Now, if m is 0, you'd be approaching along what? The x-axis, right? If m is 0, the numerator would always be what? 0. And I'd be dividing 0 by what? X squared, basically. And as x approaches 0, I'd be going 0 divided by what? A non-zero number. Even as x approaches 0, I'm going to have in the limit what? 0. Okay? Now, if m is not equal to 0, consider what happens as x approaches 0 here. As x approaches 0, even if m is a constant that's not 0, you can see the numerator is going to be approaching 0, right? Because x is approaching 0. X is going to be approaching 0 here. The denominator would be approaching m squared. But m isn't 0, so you're going what? 0 divided by m squared? Okay? Or something approaching 0 divided by m squared, and you would get a limit 0 once again. Okay? So the point is that whenever we approach the origin, right, along a line that is not vertical, we always get a limit being what? 0. I still claim the limit does not exist here. What happens if we approach along the vertical line? What's the vertical line in the xy plane? That's just the line x equals 0, right? So you can imagine coming along the vertical here. X is always 0. What is our function? X squared y over x to the 4th plus y squared. If x is actually equal to 0 at each point on that line, then we'd be going 0 squared times y divided by 0 to the 4th plus y squared. Again, y is approaching 0. It's not equal to 0. Okay? We would still have what? A 0 numerator, a non-zero denominator. The quotient would be 0 each time we take the limit as y approaches 0 of 0 is 0. Okay, so do you see what happens? So in this thing, this function's interesting, okay? You might want to actually graph this on GeoGebra or something. As we approach the origin along every straight line, approaching the origin, the limit is always what? The limit is always 0. Does that mean the limit itself is 0? No, well, unless I'm lying up here, no, it doesn't mean that. Wow. This is way different than the kind of situation that could happen in one dimension, right? Okay? This is very different here. I claim the limit does not exist. Well, how do I show that then? Well, this is kind of tricky here, okay? If we approach the origin along any line in the plane, we get a limit of 0. But how about if we approach the origin along the parabola y equals x squared? Okay? So you're going to replace what? Y by x squared everywhere in the original formula. So you're going to have what? X squared, y becomes x squared, x to the fourth plus y squared becomes x to the fourth plus x to the fourth. X to the fourth divided by x to the fourth plus x to the fourth is x to the fourth divided by 2x to the fourth. Now x is approaching 0 but is not equal to 0. What happens? I always get a half. Okay? All right? So I'm taking the limit as x approaches 0 of a half, essentially, and that limit is a half. A half is not 0. Okay? Now, why is I'm saying it's not 0 shows that it's not a limit? Well, up here, we could go along any line and we would get a limit 0. Okay? But along this parabola, we get a limit 1/2. Okay? The limit doesn't exist. Okay? The limit does not exist because we found, that's supposed to be the xy plane anyway. All right, I'm writing with a mouse and it's not so easy. Okay? But if you approach along this line y equals x squared along this parabola, it turns out that the limit, so we're coming in like this, it turns out the limit is a half. Okay? Can you see the direction of the arrowheads? They're coming in like that. The limit is a half. When I approach along these lines, the limit is what? 0. Okay? In order for the limit to exist, it's got to be what? It's got to be the same value regardless of how you approach the point. Okay? You got to have the same value regardless of how you approach the point. Okay? That's not the case in this problem. I approach along the lines, interestingly, and I always get 0. But if I play this little trick and go along this particular parabola, I get something that's non-zero. Okay? Alrighty? If you have to actually look at this function, it's weird. It has a little shelf along that parabola, y equals x squared. So I'm not saying this one was an easy one for you to do yourself, because you probably wouldn't have thought of approaching along the line y equals x squared. But nevertheless, know the lesson here, right? I could have the same value, the same limit approaching every line, along every line towards the point of interest, and get the same value. That still is not what? That's not sufficient to show that the limit exists. Okay? That is not sufficient to know to prove that the limit exists. Okay? Alrighty? Now, these are just some trick problems. We're not going to be doing tons of these and stuff. Most of our limits are going to exist and be easy to compute. But I just want you to be aware of this. Okay? Alrighty, this is tricky. Now, notice how much trickier this is than Calc 1. Again, like I mentioned in the previous video, if you're worried about a particular point, and along the x-axis, you got two ways of approaching. You can approach from the left, or you could approach from what? The right, from above or below. Whatever your x value is, say x equals a, right? And your function's up here somewhere, right? That's pretty easy. Notice the incredibly more difficult situation we're dealing with. when we're talking about multidimensional functions. Okay, again, I want to emphasize I'm not going to give you tons of problems involving epsilons and deltas and stuff, but this is stuff you need to be made aware of. Alrighty? Okay, well, I hope you understood this stuff.